Today we are going to look into one very important theorem called open mapping theorem. Uh, would you like to have a small introduction to it? Hmm? There's an important uh, matter that we have to know is the what is called and what is called the inversion of a operator. So essentially, what I wish to tell you is that if you have an operator, just 1 minute, there is some problem with the. Just 1 minute. Just 1 minute. System is creating a bit of problem. I'm sharing the screen. Just 1 minute.
Excuse me, sir.
Hmm.
Sir, the problem in screen sharing, sir, or opening any file?
It is screen sharing. One file is not closing.
Uh, I think you open in some another, sir, like in another window, maybe.
Mm. It says this WPS file says upgrade now. No, I don't want to upgrade this. So there is some issue with the WPS file. It's neither going down nor it's allowing me to upload. Can you wait for some time? I'll restart.
Yes, sir.
Just
Sure.
wait for some time.
Yes, sir.
Am I audible?
Yes, sir.
I will tell you a few things which I thought I will write, but this WPS software, it says upgrade, otherwise it's not opening. So just wait, I'll restart and then do it from PDF file. See, there are 4 main theorems in functional analysis. One is the Hahn-Banach theorem. Second is the uniform boundedness principle. Third is open mapping theorem. Fourth is closed-graph theorem. I'm talking on Banach spaces, okay? Hilbert spaces is a different story. So we are trying to do something on the open mapping theorem. One of the important aspects of especially the applied part of the mathematics, it is about continuity. Okay. I mean, what exactly I mean by that? Suppose you want to calculate root 2, right? So you create a sequence of numbers which is likely to converge to root 2. Suppose the function that we are considering is not continuous. Even if this series is, if this sequence is convergent, you can't prove that it is the value of the root 2. So this continuity is a very important aspect in numerical analysis and in many other places. For example, if you are looking at the data sciences, if you slightly vary the data, it should not happen that the output goes off in a different way. I hope you understand what I'm saying. See, you take a cup, inverted cup, and put a marble, goli kehte hai na, marble, and give a slight push to it. It will oscillate and then it will stay back inside the cup. Take the same marble and put it on the flat ground and give a small push. It will be close to it. Now what you do is you invert the cup and keep the marble on the top and give a small push. No matter how small push is, will it come back to its original position? No, it is unstable. Therefore, the situation that when you have some functions which are discontinuous, it will lead to instability. In the sense, what I'm saying is, if you have a data, right? You take a data from somewhere and you put it in the computer. When you put it in the computer, there is a certain amount of error. You can't put the data exactly. So when there is an error there, there's a small error. Suppose this error grows up because you have not put the exact value, the computations that you are going to do could be useless or invalid or a waste. Therefore, continuity becomes a very important aspect. Now, what happens is that when you take a vector space, if you take a linear operator from a vector space, say E to F, if T is continuous and T inverse exists, it is not necessary that T inverse should be continuous. Sir, why are you interested in the inverse? Inverse is the place where you actually get the solution, right? Suppose you take Ax equal to B, a set of equations that we are going to have. If you want to find a solution X, what is that? The simplest way of doing it is invert the matrix A. Suppose the matrix is not invertible, then you get into trouble, right? Suppose it's a square matrix, so Ax equal to B, if A inverse exists, then the solution is X equal to A inverse B. What if the matrix is not invertible? Then you get into trouble. That is why I am saying invertibility is an important aspect. Now, when you are looking at functions on the metric spaces, suppose f is a map from x to y, if f is invertible and f is open map, then f inverse is continuous. What is the meaning of that? It means although you have not verified that epsilon delta stuff, whatever it is you want to have, still the function f inverse is continuous. Now that is what the open mapping theorem says. You don't have to verify what is happening with f inverse because many times we may not know the inverse, okay? But what it says is if f is onto map and a continuous map from a Banach space to another Banach space y, then f inverse is continuous. It doesn't say f inverse is continuous, it says f is open. So on the range, the f inverse will be continuous because every inverse image of an open set is open. That is what is the necessary condition for a function to be continuous from a metric space to metric space. That is why open mapping theorem becomes very, very important. Okay. Now, if you have any simple, straightforward questions for this brief introduction, you can. Last time, I think I gave you an example where T is continuous, but T inverse is not continuous. The reason being that the map is not onto. I have not proved it, but that will be one of the problems that you have in one of the next assignment which is going to come up. All right, let me ask you one more simple question. Do you want anything from me for you when I come on 27th? Do you want soft copies of the books? Or do you want a hard copy of the book? If I have a hard copy, I'll come and share it with you. Hmm? So all of you are quiet, huh? All right. Now the proof of the open mapping theorem is basically based on the fact Bayes category theorem. So these three theorems, uniform boundedness principle, open mapping theorem, and Close-Cock theorem, they are based on the Bayes category theorem. That is why the course on analysis that we have studied earlier becomes very useful. We can look at it from a different angle. When you are studying Bayes category theorem, you would have never expected that you are going to use this summary here. That's a very important comment that probably you can understand here. When you study something, you feel like what is called see a place where it can be applied. For example, somebody asked me in the class, where do you use Holder's inequality? There are umpteen number of places where you use Holder's inequality. I told you earlier. To calculate the functionals on L3, L4, etc., you need the Holder's inequality. Okay. So these are issues that we have to take care. But when somebody is teaching metric spaces, they may not teach you from the point of view of function analysis. So that is why I am trying to recollect these two. Okay. Just hold. All right. I will log out of this mobile and I will join you on the computer. The computer is about to start. I'm restarting the whole system. Performance in the exam is okay, but I would have expected something better than you. Because everybody tells me that the fifth semester students are very good and whatnot. Even your director said they are very good, etc. But now I have realized one thing, that you don't have probably written notes. That is why you have problem of writing exams. Am I right?
Somewhat, sir.
Somewhat. Okay. That is what somebody told me in the last class. So what I am thinking now is, whatever I have done till now, I will send a written notes for it. I will sit down for some 3-4 days and write a clear-cut notes and then send it to you. That would be helpful for you. Okay. So
Like, sir, the notes
Go
are
ahead.
in discrete forms, and like we have to collect from some parts of this book and this book. So we miss some points, sir. That hit hard, sir.
What I'm saying is, I'm there on 27th, no?
Yes, sir.
So you can ask me. Note it on a piece of paper. Ask me what is the doubts you have. I'll clear it up. That I can do for you. Okay.
Yes, sir.
If you want something more, you tell me and let me try to do it.
No, no, sir.
Only point which I want to tell you is that take a piece of paper and a pen when you are studying the notes. Note it down. What is the difficulty you have? Then it's easier for me to help you out. Because when you come to the class, you may not remember what is the doubt you have. But if you write it down, then we can sit down and finish it. I am also thinking of meeting the first year students. I want to tell them how to write answers in mathematics. This is one more point which many people told us, that we don't know what exactly we are supposed to write or we are not supposed to write. Right? So I will tell the students that what is that you are expected to do when a question comes to you and you are writing an answer in a quiz or in a exam. You should read the question, understand it properly, and write out this is what is to be proved. Right? Now, if you don't do that, for example, the integral operator I gave on L2, but people are now looking at 0 to x1 plus x2, etc. I am not worried about the x is fixed here. X is not, the function has nothing, the operator has nothing to do with the points in the interval 0, 1. The operator opts on the functions in L2. That is what you should keep in your mind. If you miss it, then we get into some funny problems. That's what I wanted to tell. Is it worthwhile talking to the first year students
Yes,
so
sir.
that they don't get into trouble when they come to second year and third year? I don't know whether somebody spoke to you or not, but I thought I'll speak to I told your director I want to speak to our first year students and tell them what is that and give what is called a model answer for a model question. That's what I thought. Essentially, you see, this JE, etc., they make you to usually bubble the correct answer or choose the correct answer. You don't write it there. That creates a bit of a problem. That is what I am a bit worried on that. Okay. Anyway, it's not a big issue, but it's something that we have to understand is that there is a certain amount of, I mean, you should not write which are irrelevant. Why I am saying you should not write, you can write, I don't mind, but you lose time. But in an examination, the time is fixed. You don't have great time, right? That's the reason why I am saying that you have to be a little bit careful, essentially the examination part. So the computer is slowly starting now. I will log out from here.
So I'll share the screen and then come back to you. Can you see the screen?
Yes, sir.
So this 4.12 is the open mapping theorem. And I told you it is one of the important aspects of the open mapping theorem. So a few comments which I have made, I will detail it on Wednesday. So definition of open mapping, this I had given you last time. Let X and Y be a metric spaces. Let domain of T be the domain of T. Then T from dt to Y is called an open map if it maps every open sets of dt to open sets in Y. When you say open set in dt, it's a subspace image, okay? All right. So what is the open mapping theorem here? I will increase the font slightly. Or it will become too big. Yeah. Open mapping theorem says that it's also called bounded inverse theorem. A bounded linear map T from a Banach space X to a Banach space Y is open if it is onto. Okay. A linear map T from Banach space X onto a Banach space. This onto is important here in the. So if T inverse is bijective, that is if T inverse exists, then T inverse is continuous. Continuous, or in this present case it's bounded. Okay. So there is some issue with boundedness here. I don't know whether I should tell you. Okay, I'll tell you what is this problem with the boundedness that we have. Okay, just hold for a moment. Huh? Just 1 minute. In the examination paper, whatever I have seen, there are some issues. It's a confusion about the boundedness. That is where I'm a bit worried. So I thought, let me show you today what exactly we mean by bounded. Okay. If you have any doubts, please let me know. Okay. Can you see the screen?
So
You see, this boundedness is creating problem for you. Okay. What it creates the boundedness. See, the problem is that our understanding of boundedness is this. Suppose F is a map from R to R. Okay. We mean that F is bounded as a function. If there exists an M such that mod fx is less than or equal to M for all x in F R. Is this what you know about the boundedness? Now, when you look at,
Yes, sir.
okay, when you look at F as a map from a vector space or a Banach space, so this X is a Banach space, okay? And F is linear, we say F is bounded or continuous if F maps bounded sets to bounded sets. This is as good as saying that this mod norm of fx is bounded if norm of x is bounded. This is the boundedness. It's not this boundedness. Huh? So if you take a linear operator, for example, you take a linear operator from R to R. How does it look like? So if you look at Tx, it will be nothing but Ax. Right? These are the linear operators. Is it bounded? T is not bounded as a function, but T is bounded as a linear operator. Is it clear? You have to be slightly careful here. Okay. Why I am saying is that the example that when I said that F is in L2, this is the example, the problem that you have. And what I said is show that F is a map. So this is your X. F is a map from X to X and F is bounded. Now most of you, the F is given to be, so this T is given to be T of F at X is defined by 0 to X S F S ds. Now what people have understood is that the domain is X. Domain is not X. For F in L2, TF is in L2. What do you mean by TF is in L2? You have to, it's a function from 0, 1 to R, okay, such that integral of mod fx squared is finite. 0 to 1. But the domain of T, this domain of T is L2, not R. Many have mistaken that for R in the examination. That is where it makes me a little bit unhappy. Now, second thing is they have said you look at mod of Tfx that is less than or equal to the L infinity norm. This is correct. L infinity norm of f, that is okay. Okay. That doesn't mean that T is bounded. That doesn't mean T is bounded from L2 to L2. This only says this T is a map from L2 to L infinity. That is bounded. This part. Not L2 to L2. Is it clear? Now this L infinity, I don't know why you have taken this L infinity as a boundedness for this operator. You have to calculate the norm of T in L2. That is what you have to do. But you are not doing that here. You are looking at this operator T as a map from L2 to L infinity. No, I am not talking of this operator. The question is, it's about L2 to L2. Okay, it's a map from L2 to L2. Is this clear?
Yes, sir.
And I think this has created a lot of discrepancy in your head. And when it comes to function space, you are in trouble. When you come to sequence spaces, you are in trouble. You don't know whether it's a function space or a sequence space, but you treat all of them as the real numbers. That is the one issue I have noticed it. Any questions on this point you want to further clarify? Anything you want to clarify further?
So
Yeah. No? Okay. Again, I'll talk to you on 28th when we meet. All right. Now coming back to, I'll share the screen again. Can you see the screen? So the open mapping theorem says that if T is a map from X onto Y, then this T is a is an open map, or the T inverse is a continuous map if T is bijective. So this proof is slightly longer. So what one does is you try to do a bit of simplification by proving it in 2-3 parts. Okay. So the first part that you show is that you do it on a smaller level. Okay. And then you go to a higher level. That's the just 1 minute. What do you mean by that? You see, this whatever we do in life, we also do it here. Only thing is we don't say it, right? Now, suppose you want to eat lunch, and suppose the whole lunch is served on a plate. How do you eat that lunch? Do you take the plate and then put it on your mouth? No. You take small pieces of food, whatever is in the plate, whatever you like, and then you put it in your mouth. That's the way that we do. The same way, if the theorem is slightly bigger, then we split that theorem into 2-3 parts and then give the proof for each part. That's the advantage of splitting the proof. If you are a teacher, you have an advantage. You can give the part of the proof instead of the whole proof in the exam. Nobody will ask you the whole proof of the open mapping theorem in an exam because it is too, I think it's not a good idea to ask the proof of the whole theorem. Okay. So the first part of the theorem is the following. We prove it on the open unit ball. And then we come down to the whole thing. So that so this is the lemma that we are going to do it. This is called the open unit ball theorem. A bounded linear operator from a Banach space X onto Y has the property that the image of T B naught. What is the B naught? B naught is the open ball of radius 1 with center 0. If you look at the T of B naught, that's the image of T B naught, then it contains an open ball around 0 Y. See, if 0 is in B naught, then T0 will be 0. So if you look at the image of T B naught, then it turns out that around 0, it has an open ball in Y. This is true only if the map X is onto. Note, read here, Banach space X, this T is a map from Banach space X onto, this is important. Huh? Okay. So I hope you get my point. I am referring to this onto-ness here. Okay. This onto. This onto-ness is important. Okay. Okay. All right. Now, how do you proceed the proof of this? The proof is done step by step. Now here, last time I also gave you, in this proof, there is a certain notation that is used. This notation is not going to be used everywhere. So be careful about it. So B1 means it's a ball around, all the B's are balls around 0. B1 means this radius is half. B2 means the Bn means the radius is 0 with the 2 raised to minus 1. So this is 2 raised to minus 1. B2 means the radius will be 2 raised to minus 2, like that. So the closure of the image of the unit ball, okay, the closure of the unit of ball, this, whatever this ball B1, it contains an open ball in B star. Okay. All right. The TBN closure, that is the closure of this ball B0 2 raised to n, contains an open ball Vn, some open ball of Vn, we don't know what the radius is, with center at 0, such that this Bn, whatever this Bn, it is contained in B of 0 2 raised to minus n, and that is contained in X. So this ball Bn, that whatever we are talking, okay, it is in this particular, this equal to this, it is contained in X. That's the point. Third C part, TB naught contains an open set about 0 in Y. But these are the three what are called preparatory lemmas or preparatory theorems for proving the open mapping theorem. So you prove one A, B, C. First you prove A, second you prove B, third you prove C. So how do we prove this theorem? So you need some notations here. Alpha A, these notations I have given. Okay. So I'll send you this part of the notes to you. So we consider the open ball B1 with radius half with center at 0. You fix any X in X. Then you look at, then it is in KB1 with the real K. That's an obvious thing if the K is large, right? I mean, this point, you fix any X in X, it has to be in some ball of radius, whatever the radius is, okay? We don't care. So it will be, what I'm saying is that when you take the ball of radius 1 multiplied by K, it becomes a larger ball of radius K, right? It is dilation. Multiplying by K with B1, you get a dilated ball of radius K. So if K is large, obviously this point, any fixed point X is in this one. This is because of the fact that X is actually K equal to 1 to infinity KBN. This follows. And therefore, X is a union of some sets. Now, the moment you write X as the union of some sets, so you are actually trying to bring in the what is called the Bayes category theorem. Okay. Since T is surjective, so T is surjective, so Y will be T of X, that is correct. And that is same thing as T of union of all these balls, that's also correct. Now, this you can show it by set theory. This union you can take out, K equal to 1 to infinity, KTB1. That can be done. And KTB1 is contained in KTB1 closure. Therefore, this is also contained this because it cannot go beyond Y. So that's an obvious step. Okay. Note that by taking closures, we did not add any further points to the union. We are saying we are not adding any further points to union, not to the set. You have to be careful here. Okay. What it says is you don't add any more points to the union. It is not that KTB1 closure is KTB1 is KTB1 closure. No. But when you take the union, it turns out to be same because the whole thing is in Y. It cannot go out of the Y. Right? So you have Y to be the union of such closed sets. Now, there okay. Since Y is complete, it is non-meager. Y is complete, non-meager means what? There is at least one, if you take a union of that set, at least one set will contain a non-empty. The interior is non-empty. I told you meager is also used in the word thinness. It's not thin. So at least one of these sets will be thin, because if it is not thin, if there is no interior here, then this Y cannot be complete. That's the base category theorem. Okay. Hence, noting that 3 is similar to 1, whatever the previous thing is, we conclude that at least that KTB1 must contain an open ball. So this KTB1, whatever we have here, for some K, whatever that K is, it has to contain an open ball. Say B star. So call this as B star. B star equal to B of Y naught epsilon. Where is that ball situated? That we don't know. So call that ball with center Y naught and epsilon as Y. Now, if the ball is at Y naught, you translate it by minus Y naught, it becomes a ball of radius epsilon. This is the simple calculation of the first part of the theorem. Okay. So it is 56. All right. So you go for your lunch. I'll send you these notes. And next time, that is tomorrow, I'll finish the proof of this theorem. Okay. All of you, you go for lunch. Have a nice lunch and enjoy yourself. If you want anything from me when I am coming there, you please either send a mail or send an SMS. Okay. You have a group ID and you can send an SMS to me on that. Have a good day. Bye.
Yes, sir.